Okay, so an angle is in the standard position if it is drawn in the XY plane with its vertex to the origin and its initial side on the positive x-axis. So, for example, this is an angle in standard position. Okay, its initial side right here. It's on the x-axis. Terminal side right here. Okay, it is made by creating that angle there. So that's an example of an angle in standard position. This is another example of an angle in standard position right here. Initial side, maybe I rotate more than one full time around and I create an angle of this form. As long as that initial side is on that positive x-axis, we can create an angle in standard position. This is not an angle in standard position, however. Not an angle in standard position, its initial side is not on the positive x-axis. Okay, two angles in standard position are coterminal if their sides coincides. So think about if we have an angle, okay, maybe it's 30 degrees. Is there another angle that has it so that the sides coincide? Well, actually there is. If I have a 30-degree angle that's in standard position, right? Maybe that's 30 degrees right here. Is there another angle that we can create that has the same situation where the initial side and the terminal side line up directly? Well, sure, I can do this. Right there. So that's a full circle, 360 degrees plus 30 degrees, that'd be 390 degrees. Okay? So 390 degrees is another one. But you could also go 360, 360, and then 30. So there's another infinite list of angles that can match up with the same one, so that are coterminal, in other words. So we could have an infinite list, say 30 degrees, 390, okay, add 360 to that, and then you get what, 750, dot, dot, dot. But you could also go backwards, and you could get negative 330 at subtracting 360 from this, and we get an infinite list of angles that are coterminal. So now we have theta equals pi over 2. Find angles that are coterminal to it. So pi over 2 angle, right? Pi over 2. So what are the coterminal angles to pi over 2? Well, pi over 2, you could also go 2 pi plus pi over 2, which is 5 pi over 2. Or 2 pi plus 2 pi plus pi over 2, which is 9 pi over 2. And you can go backwards with it as well. So we have this another infinite list of coterminal angles. Okay, so the length of an arc is proportional to the size of its angle. Okay, so in other words, as theta gets larger, so does this arc, right? So what we can say is theta is to, that angle is respective to the measure of the whole angle that would represent the whole circle. So theta is to 2 pi, that ratio. This portion of a full circle is as this length is to the length all the way around. What's the length all the way around? The circumference of the circle. Okay, 2 pi r. Again, this portion of a full circle, this angle of a full circle, is to 2 pi all the way around for an angle, and angled all the way around, is as this length of this arc is to all the way around, which is 2 pi r. So if we, the only time I'll ever say this is cross multiply. I hate cross multiply, but anyway, if you cross multiply, you get theta times 2 pi r equals 2 pi times s, divide both sides by 2 pi, you get theta times r equals s. So in a circle of radius r, the length s of an arc that subtends an angle, central angle of theta radians is given by s equals r theta. So this right here tells us the length of a circular arc. Okay, so we're trying to find an area of a sector. So what's the area of this sector? Well, that's a fraction of the whole pizza, right? It's a fraction of the whole pizza. It's a part of the whole pizza. What fraction is it? Well, it's theta over 2 pi. This portion theta over 2 pi. That's what fraction this piece is of the entire circle. So if we multiply theta over 2 pi times the area of a circle, pi r squared, notice the pi's cancel out, and this ends up being 1/2 theta r squared. So this is the fraction of the whole circle. Okay, so the area of a circular sector then is 1/2 theta r squared. Okay, so now we're going to talk about linear and angular speed. Suppose a point moves along a circle of radius r, and the ray from the center of the circle to the point traverses theta radians in time t. If s equals r theta is the distance the point travels in time t, then the speed of the object is, and there's two speeds here. We've got angular speed here, okay, and we've got linear speed. What is angular speed? Angular speed is how fast the angle changes, whereas linear speed is that how fast that point on the circle goes around. Okay, so let's take a look. A boy rotates a stone in a 3 feet sling at the rate of 15 revolutions every 10 seconds. Find the angular and linear velocities of the stone. So the angular speed, 15 revolutions in 10 seconds. Okay, so if we do 15 revolutions, that's 15 all the way around, right? So 15 2 pi's, so that's actually 30 pi radians. So if we have omega, which is the angular speed, equals theta over t, and we do 15 revolutions, theta, if we have theta equals 15 times 2 pi, because we're doing 15 of the 2 pi, that's what the whole circle, that's a revolution, is whole going all the way around the circle, divided by the 10 seconds. Okay, so then what we'll have here is we'll have 30 pi divided by the total time of 10 seconds, which equals 3 pi per second. Okay, so 3 pi radians per second. I didn't put radians there, it should be radians per second. Okay, radians per second. Okay, so that's for angular speed. Okay, now let's talk about the linear speed. The linear speed of the point as it goes around. Okay, how fast is it going around? Okay, well, what's the distance that it travels in 10 seconds? Well, the distance that it travels in seconds is 15 revolutions. Okay, 15 revolutions times 2 pi r. 2 pi r is the circumference around. So 15 of the 2 pi r's, right? Which is 30 pi r, right? 30 pi r. Okay, so s, in this case, is going to equal 30 pi, okay? And a 3 feet sling, so that'll be times 3 is my radius, my sling, radius 3, okay? So my sling of radius 3, and then I'm going to divide that by, oh sorry, that's my s value, is 30 times 3, 30 pi times 3, so it'll be 90 pi. And so v, the velocity v, equals s divided by t, so it'll be 90 pi divided by my t is 10 seconds. So this turns out to be 9 pi feet per second. Okay? And I don't know if you can even see that. A little bit lower. There we go. Okay? Good. Okay, so now let's talk about the relationship between angular speed and linear speed. Okay, so if we know v, linear speed v, is s divided by t, and we know s, okay, is equal to r theta, well then that means r times theta over t times r, that's what this is. Well, isn't theta over t equal to omega, the angular speed? So then we'd have this will equal r times omega. And so the relationship between angular and linear is given by v, the linear speed equals the radius times the angular speed. Okay?